Assalamualaikum warahmatullahi wabarakatuh, and a very good day to Dr. Najib, Dr. Ahmad Najib, and Zakaria. And today, my name is Ahmad Ibrahim, and today I'm going to present my findings on the Quasi one-dimensional Nozzle flow project. So, in this video, I'm going to touch only a few parts of my project, which is the introduction part of the OC one-dimensional Nozzle flow, a little bit on the governing equations, and the numerical algorithm, which is correct technique, and also the numerical results. So in this quasi one-dimensional Nozzle flow, uh, we are going to consider the isentropic flow through a convergent divergent nozzle, which its shape is predefined by a parabolic area distribution, which is given by this equation. And then uh, for A at standard conditions, the specific heat ratio will be gamma is less than 1.4. And then this is some of the functions of the flow fluid variables that will be used in calculating the initial conditions to be computed uh, for the next time steps in the common technique. So this is the some of the derivations of the governing equations, which will include the continuity, momentum, and also energy equations. So for each of continuity, momentum, and energy equation, I'm going to consider the same nozzle slice with infinite zero thickness of the slice AX as the control volume. So this will make the derivations of the governing equations easier. So as usual, the continuity equation will have us to use the fundamental physical principle, which is mass is constant, where we will start at the from the integral form of the continuity equation, and after some um, physical applications and some algebraic manipulations, we will have the continuity equations as equation 2. And then for the momentum equation, like, as I said before, we are going to consider the same nozzle lines, in which we will derive the momentum equation from the integral form of x component of the momentum equation for an invisible fluid with low body forces. And this is the conservation form of the momentum equation, and I also include the method on how to convert the conservation form of the momentum equation to the conservation form, where we will need to multiply the continuity equation V, then subtract the result from the conservation form of the momentum equation. And then for the energy equation, I'm not going to derive fully, because the approach is just the same as in related equation. And this is the non-conservation form of energy equation for the quasi-dimensional fluid. And then for the uh, computation purpose, uh, this is the part where we don't want to bother with the units of the four-field variables such as density, velocity, area, and so on. So this is where we will make the governing equations to the dimensionless form, in which this is the form of the continuity equation, and this is the non-dimensional expression, and also energy equation. So let's dive into the micromet technique, which we will have five steps, which is predict the step, uh, where we will replace the special derivative with form difference, and then we calculate the predicted value, the correct step, uh, where we will replace the special derivative with backward difference. We take the average between predicted and correct step, and finally we will have our approximate value obtained from the macro method. So this is, as I said before, the predicted step for the continuity equation. So this is the predicted step, the corrected values, the predicted step. So um, let us illustrate on how we can compute the flow fit variables using a Markov technique. So we are going to consider the flow fit variables at x is equals to 1.0. Before that, let's consider the nozzle shape. So I've uh, plot the nozzle shape by using a pen, where I use the um, matrix for the area, density, temperature, and velocity, and I also calculate the nozzle shape as a function of spatial property. So and then I plot the nozzle shape by using MATLAB, and this is somehow what will the nozzle shape will look like in real life, but it's not really accurate because in some cases, uh, for example, if you go into the afterburner of a firefighter jet, it will uh, not similar as this nozzle shape as I have shown in this nozzle flow project. And then I was asked to tabulate the initial conditions at t is equals to 0, where this is the initial conditions that will be used in the micromet algorithm. So let's dive into the micromet technique illustration. So in this case, this is the correct steps for the density. So I might have noticed that I have some mis type here. This is supposed to be density del rho or del p at as I is equals to 11 at time t is equals to 0. And then also the predict, predict the step for the velocity and also the temperature. And then this is where I calculate the corrected values, and then this is the correct uh, I'm sorry, this step is the predicted values, and this one is the correct steps. So as you notice in the correct steps, we don't have the value of v bar, rho bar, and t bar 10 at I is equals to 10. So we will have to calculate this value at the special value I is equals to 10. So after some computations, we will need to stop at the corrected values, because these values will be used in calculating the correct steps for I is equals to 11. So this is what the the correct the predicted values from the I equals to 10. So I've substitute all the values here, and this is the values that I get from all the calculations. It might not be accurate as in MATLAB, because calculation, and there might be some error in where I miss type it in the calculator, and also the number of decimal places might contribute to the error in my calculation. So after that, uh, after all predicted steps, predicted values, the corrected steps and corrected values, finally we can calculate the value of the flow-fit variables at x is equals to 1 to 0. So this is the flow-fit variables after one time step, where I compute it by using MATLAB, where the MATLAB coding will be attached at the end of this report. So this is the timeless variations plot of the flow-fit variables, which specifically on density, temperature, pressure, and Mach number. So this is the comparison of the density at the nozzle throat and the nozzle end. And this is the timeless variations comparison for temperature, and this one is the timeless variations comparison for the pressure, and the timeless variations comparison for the Mach number. So this is the plot of the non-dimensional mass flow rho times v multiplied by a through the nozzle at different time step. So as you can see, the legend says that 0 dt, 100 dt, 150 dt, and so on until 3000 dt. So dt indicates that after 0 time steps, what will happen to the non-dimensional mass flow. After 100 time steps, what will happen to the non-dimensional mass flow until 3000 time steps. So this is the flow fit variables after 3000 time step. So last but not least, this is the comparison of density, temperature, pressure, and number at the nozzle throat and nozzle exit with different pressure step sizes. As you can see, let's focus on the Mach number. The Mach number uh, will increase as it goes from the beginning of the nozzle until the end of the nozzle. As I have said here, the Mach number starts at less than 1 at the convergence section of the nozzle, which is the convergence section of the nozzle, and increase throughout the nozzle. And if we draw a straight line from the non-dimensional distance through the nozzle at x is equals to 1.5, if we draw a vertical line to this straight line, we can see that at the nozzle throat, the Mach number will be 1.0. So I think that's all for my presentation, my findings on the nozzle flow project.